Good afternoon. My name is Shikuku Olayo, and today I'm going to take you through the project that me and my group mates are currently working on. The project is titled Graph-Based Reasoning for Large Language Model for Personalized Higher Education Support. In this project, we aim to tackle the significant challenge of for university prospect students, that is navigating the complex landscape of higher education to make informed decisions for their future. Over the next 12 to 15 minutes, I am going to guide you through our research journey. We will begin with an introduction to the core concepts and the problems that we are set to solve. We will discuss the related academic works that informed our approach, followed by the research questions and objectives that we used to come up with the approach. After that, we will dive into the technical core of our project, the methodology, the system architecture, and the mathematical foundations. We will describe our dataset, present our results, demonstrate the project that we developed, and finally, we will conclude with our project's limitations and visions for the future. To understand the project, it is essential to be familiar with the key technologies that we integrated. At the heart of our system are large language models, or LLMs, which provide a deep semantic understanding of human language. We combine this with graph-based reasoning, a technique that allows our system to make logical inferences based on the structured relationships connecting occupational occupation to skills and skills to courses. This forms the basis of our this is going to form the basis of our knowledge recommendation system. The ultimate goal is to provide an AI-driven university admissions guidance guzzling chatbot. To ground our work, we conducted a thorough review of the existing literature. We analyzed the key papers and strategic knowledge graphs and LLMs for the previous recommendations and tutoring systems. For instance, Wang 2023 showed improved accuracy by adding a knowledge graph or graph-based reasoning and demonstrated the effectiveness of the KG for AI tutors. However, our analysis revealed a, a consistent gap. Most existing systems are not tailored to a specific educational context of Uganda. They often look they often overlook deployment resources, they often overlook the constraints on like dev, on deployment, and they lack the interoperability in the resource recommendations and do not provide comprehensive admissions guidance beyond simple course matching. This is a gap that we aim to fill. In this slide, I'm going to talk about the domain application and the constraint application and the computational problems we aim to face, that we aim to solve. For the domain application, students in Uganda face significant difficulty in identifying the suitable academic programs. There is an inequitable access to expert guidance, leading to suboptimal career decisions. Current systems lack the interoperability and adaptability needed for this context. From a computational standpoint, the challenge is to design a scalable, context-aware system that can reason over complex educational data while operating under resource limitations. We were faced with the difficulty of enabling the model to effectively retrieve data from our knowledge graph, and the challenge of building up a comprehensive data sets that can align all of this data that we had collected. To address these problems, we set out four primary research objectives. First, to design a hybrid architecture combining an LLM with graph-based reasoning, and second, to evaluate its performance in accuracy, personalization, and interoperability against traditional baselines. Third, to optimize the model for resource-constrained deployment, and finally, propose a framework for ethical and explainable deployment. These objectives guided our research questions, such as how can you optimize the complex models for low cost, low latency, and low latency environments, and how can graph-based reasoning provide interoperable justifications to, to improve the user trust. And our work produced three key contributions. First, we built a modular system based on graph-based retrievers like GRAG and VGRAG to enrich our user feedback and provide accurate context. We then, managed to examine and explain free open source LLMs, especially Flantify and Llama, across the APIs that we used. That was Grok API to ensure a cost-effective solution. And a third, we constructed a knowledge graph using NetworkX. It's a Python library that enables us to establish rich relationships our data and able to join our data. That is because we had three sets of data. That is career literature, university guidelines and policies, and other university programs and cutoff rates. So we're able to use the knowledge graph to combine everything. This slide, we have the illustration of the system architecture that we use to produce our system. The process begins when a user query is submitted. Our custom graph retriever takes a query and identifies the most relevant nodes and the relationships within our knowledge graph. It extracts the focus subgraph, then provides rich factual context. This subgraph is then passed into our fine-tuned generator model, that is Google, either Google Fluency 5 or Llama, that synthesizes the information into a coherent, human readable, grounded response. This grounding on the knowledge graph is crucial for minimizing the errors and ensuring effective and accurate information from our system. For the mathematical concept, our literature is built on a robust vector space graph models and constant similarity to measure the relevance between a user query and the entities in our system. The core, the core of our system is graph theory, which structures our data into nodes like universities and courses and edges that represents the relationships within those nodes. We're able to develop very many advanced retrieval models. Our hybrid retrieval scoring function showed here combines vector similarity with graph-based reasoning to enhance and rank results, ensuring semantic and contextual accuracy. Then our models employ graph retrieval techniques from a simple neighborhood extraction into a multi-hop reasoning, which allows us to find complex and non-obvious connections between a student's interests and the potential academic path. And then for this third graph, we use the Krag model that excels which excels at like subgraph extraction, creating a small relevant graph to 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 provide on-the-fly context for the LLM. The KAG model focuses on pathfinding using excellent reasoning chains to explain these recommendations. The key was to ensure modularity in our research, allowing us to test and modify these these systems effectively. Moving on, I'd like to talk about the data extraction and data and the EDA. A model is only good as its data. We constructed a unique data set by combining career data from nets. It's a website online that gives jobs and like the skills required of those jobs, and also the comprehensive PDFs that we managed to get from the Makerere University website, and like you named and and you're gonna be of statistics. The dataset constrains critical information like program details, cutoff rates, required subjects, career paths, and in total, our dataset consists of 922 records with 19 distinct features, which provided a rich foundation for our graph-based reasoning. As you can see from this slide, our data analysis yielded very valuable insights. This top chart shows the proportion of university programs over the 10 universities, giving a clear view of institutional specializations. The book's plot shows the distribution of cutoff rates, allowing us to see how competitive the different fields are. Like you can see the cutoff rate of medicine is quite higher than the cutoff rates of 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 like natural sciences. Then the heat map here you see it shows the critical data that is missing, that we had to carry out some pre-processing in order to address the missing data fields, and so the knowledge graph can be more accurate. Then using Network X, we're able to construct our graphs, which you can see here. They show the semantic subgraph, which you can see actually the semantic subgraphs that we created. Like for example here, it shows the Bachelor of Medicine and the Bachelor of Surgery. Each connected node represents a closely related entity from universities like Barara, also related to required skills like hand-arm steadiness and related works like physician and anesthesia. And this is rich and interconnected. This rich and interconnected web of knowledge helps us navigate and provide insightful answers that maintain interoperability and flexibility to the user's query. Then to validate our system's accuracy, we conducted a quantitative evaluation, as you can see from the graphs here. As you can see in these tables, our model's predictions align remarkably well in the ground of truth. For questions about career paths, program duration, or required skills, the model provides answers that are both correct and contextually relevant. For example, it correctly identifies the Bachelor of Law is 4 years long and that a computer science degree can lead to a career like software engineering or data scientist. We also performed quantitative analysis for the different retrieval methods. The detailed performance metrics that chart clearly tells a story. While a simple model like CGR had fast response time, it poorly scored on the coherence and completeness. In contrast, our other models like CAG, GRAG, and VGRAG achieved higher performance scores in coherence, completeness, and accuracy, while maintaining extremely low response times over virtually 0 seconds. This determines the efficiency and effectiveness. So based on the comprehensive evaluation, we selected our optimal architecture to be Llama, the large language model, and combined with a VGRAG retriever. This combination provides a balance, accuracy, interoperability, performance, and resource constraint evaluation. We're able to deploy the project on a website called Model, called create a website like a server called Model, and we're able to connect this server to our front end, which we used to build using React Native, and we were able to do that using the API keys we created using Fast API. See, the designed the design that we help on we plan on incorporating for our model. It The user can interact with a conversational AI, answering questions about their interests, career aspirations, and constraints. And in the background, our system will be building a user profile, querying the knowledge on the graph. The system then returns a personalized recommendations like engineering, electrical engineering at Chambago University, and explains why it's a good match. It also generates a personalized academic career graph, usually connecting the user's profile to the recommended course and potential careers. This leads to a better decision making and more intuitive decision making. While we are proud of our results, we recognize that the project had limitations. The system's effectiveness is directly tied to the accuracy and the completeness of the knowledge graph. The FLANTI5 model was finite and context had a finite context window, and unlike all other LLMs, it was incoherent and it didn't give in-depth analysis of the data. Additionally, the graph retrieval on the large-scale graphs could be computationally intense. We we have proposed our practical suggestions like to migrate each of these, such as implementing robust data validation pipelines and conducting these basis through audits, and also like batch processing to help us like to break down the data so it can be computed easily. In conclusion, we successfully designed, implemented, and evaluated a novel system for personalized higher education and decision support. We demonstrated that combining graph-based reasoning with LMs can provide accurate, interoperable, and efficient guidance toward tailored education decision in the Ugandan context. Looking ahead, our future work will focus on exploring more sophisticated neural networks, developing dynamic and multi-hop retrieval strategies, and systematically addressing biases in both the data and the models to ensure equitable and fair decision support for all users. Finally, on behalf of our team, I would like to extend our sincere gratitude to our supervisor, Mr. Marvin, for his continuous guidance and support. We thank the Department of Computer Science and Makerere University for providing us with the resources and the opportunity to carry out this research and project. Thank you all for your attention. Have a good day.